Okay, so then you have after diagnosis you have procedure codes. So procedure diagnoses are different, but they are available at both the same website here. So after procedure codes, you have procedure day code. It tells you when this procedure was done. Let's say a procedure X is done at day 5, you'll be able to figure out by using this day. It's a bit tricky, but once we do a bit advanced, I'll let you guys know how to do it. And then afterwards, all of these codes are self-created. So they don't they're all created from diagnosis codes. So they didn't exist before. The regional code is created from the NIS stratum code. It's a single 4-digit number, that alphanumeric digit that codes the location, what kind of hospital is this? Is it an urban or setting hospital? What is the size of the hospital? 250 beds, 750,000 bed, and which region? So until 2011, there are 4 regions, and afterwards there are 9 regions. These are comorbidities. Again, they are all created from ICD codes, but these are standard comorbidities that HCAP provides in their manual. Then we have again all of the other variables, they were manually coded into this data set. So this is your data view. In this you can see these are your number of patients on this side. Variable views just tells you all about variables. You can search variables on this tab by just using the search icon. You can see this is the variable label. So what label it has, you can also search this on this icon. Um, So this means that for basically what you'll be looking in NIS will be your cost. This is why it was created originally. The cost variable, you'll be looking at length of stay. It's stated LOS. This is your length of stay. And then any diagnosis that you can pull off from the diagnosis history. It also has gender, race, income. So your income is here. So median house income. Also, you can also figure out the pay status. So Medicare, Medicaid, what kind of data, um, who is paying for the hospital bill. So these are the basic stuff that you can pull off from this data. Now, for analysis, if you are, so they are basically, most of your analysis, the simple analysis are descriptive. You're just doing a simple number. You want to find how many people have end-stage renal disease. So you can just do run a frequency. So that is going to be here. Analyze frequencies, and you just run a particular number. How many people have died? It's going to give you a number among the total subset. But rarely you're going to use this kind of analysis because you're always going to use a comparative analysis. So you're going to analyze. Comparative analysis is always a cross tabulation between two different things. So what I do is mostly the thing and group variables. I put in the columns and then everything else in the row. For example, if you're comparing a population of atrial fibrillation, you put them in the column. And then if you want to look at how many people died in AFib versus non-AFib group, put it here, and then you statistics, multiple options. People are using mental Hansel a lot these days, but I still stick to the Pearson chi-square, the standard. But you can use other stuff as well. You can also do correlations, but I simply do Pearson chi-square even these days. And then in the cells, you can either get column percentages or row percentages. I'm not going to do both so you guys understand which each one means and which one is more useful. So again, AFib group is 1, non-AFib group is 0. 1 is always going to be yes and 0 is going to be no. So an AFib population, 96% didn't die, 3.9% died. In non-active population, 98.1% didn't die, 1.9% died. And then you have a Pearson chi-square here. If you find an exact, that's basically done when the data set is too small. So that's an adjustment. Here, the adjustment is pretty much the same. The Fisher test and the Pearson chi-square test will be equal because the data size is large. So this is most of your tables that you see. Mostly it's grouped. This is like a TAVR data set. So you can just compare TAVR population through the same method. However, this is pretty cumbersome because you have to do individual data. So to kind of counteract, you can do complete tables altogether. So in complete table, again, the concept is the same. You take your, so this is a TAVR population. Within a TAVR population, you want to, let's see, compare male and females. So you put your comparison population on the column side, then you slide all of your numbers that you would need to do. So for example, I want to see mortality. I want to see discharge disposition, which is this variable. I want to see, for example, race. Then I want to see income. So I'm just using control down so I can select multiple things at the same time. Then I just drag all four. So you can drag unlimited stuff, and this is how you get it. Yeah, we can also select the test in the same thing. You can do independence test, which is chi-square test, and then you can also go and get percentages done. So the way you get percentage, you click this table, highlight it, then you go to summary statistics, and then you select column percentages. Apply to selection. Okay, you run an okay. So now you get like a table. So you can see that in females, the mortality was 2.5. In males, the mortality was 1.9. So this is how you got the complete table. So now you simply copy paste this table into your Microsoft Office or Excel. What I usually do, I usually copy paste it in Excel. So when I copy paste it in Excel, okay, I think I did it wrong. Like this, I can now simply combine these two columns with able bits. That's when I use this. So I go to merge the columns. I use this in between the columns. And so my columns are combined. Now I can simply paste like, for example, discharge disposition. I can copy all and paste it in an already formed like table. Like this is a table that, let's go to an actual table. So you have, for example, this table. So I can paste the data here like this. So it's usually a 2-column data. So I can just paste it like this. And then at the end of the day, when I'm done, I can simply replace the 0% or anything, depending upon the format of the journal, to like this. And it's going to replace all these three. I can do replace also. So it has kind of fixed this data already. This is how I kind of paste in. Like I create an empty table and I simply copy paste from there. So once you get used to it, it's pretty fast. So that's your simple analysis. It's just creating a simple table. The second thing of analysis that you'll be looking at will be calculating means and medians. So all that analysis that I show for you is only for categorical variables. For continuous variables, you would need to calculate mean or a median. So to calculate a mean, there are multiple ways to do it, but you can simply go to analyze, compare means, and get a mean here. So what would be an example of mean? Age. Age is your dependent variable, and the two groups that you want to compare, let's say AFib, it's going to be your independent variable. In options, you select mean. With mean, you usually select standard deviation, which is here. And then ANOVA is the test of independence. Basically, whenever you're comparing two groups, you want to make sure that they're independent of each other. They are not related to each other, meaning there's no correlation. That's what test of significance means, right? So, so this is your significant value. This is your mean square. But this is what I think you should forget about everything else for now. This is what really matters, significance. And these are your mean values. So in this TAVR population, the AFib group was older as compared to non-AFib group by comparison of mean. See, like mean in non-AFib is 79 and AFib is 82. But a lot of times they'll ask you to do medians instead. So medians are done from here because it's mostly done initially to explore data, but that doesn't apply here because data set is very large. We assume it's going to be bell-sized data, so bell-shaped data. So you don't need to worry about data. But if you have a smaller data set and you're doing a different kind of analysis, like let's say it's a hospital analysis, a small 500 patient set, then you have to use this first to see what kind of data you have. So in Explore, you click again, AFib is your independent and age is your dependent. We're doing medians here. We did mean before. And you go to statistics. You want to know about percentiles. That's what median is. Remember 50 percentile, 25, 75. And I'm going to select both here, but you can simply select statistics in the future. I'm just going to try to show you what I mean from examining a data. So if you have, so this is going to tell you, so in age here, the median age was 82 and 84. So you can see it's different from mean. A lot of journals are going to ask you to provide median age because it gives a better idea about how the data set is. By looking at mean, I cannot tell how the data is. By looking at the median, I can clearly say that most of the patients are above 87. That's the higher group. And there are very few patients in the lower group. But by mean, you can't say anything. That's the benefit of of this mean. Like most of the group, like 75% of the population is between 75 and 87. You can't say that when you're looking at mean, but you can say that by when you look at standard, when you look at medians. Now, and this is what I meant from bell-shaped data. You can see the data comes like goes up, then kind of goes down a bit. So it's not a complete bell shape, but almost a bell shaped data. This is a leaf and stem diagram. So for all of these analysis, you have to assume that the data is a normal data. But this doesn't really apply to NIS because the data is very large. So this only applies for smaller data sets. So if somebody gives you another data set in the future to analyze basic analysis, you would need to run this first. Again, this is the same thing. So that's median. So median, mean, and basic cross tabulations. That's your first thing that you need to do. Now, the second step is regression analysis. There are two types of regression analysis that you're going to encounter. One is linear regression, one is binary logistic regression. Binary logistic regression is what they usually call here multiple regression. Before you do, so regression is simply a mathematical cross tabulation that tries to tell you what are the association between different variables based upon assumptions. There are like 20 different assumptions, and these assumptions must hold true for regression analysis to work. One of the assumptions is that the factor that you're looking at, for each variable, there should be at least 20 events. So if you have 10 variables, you need 200 events. That is the reason when you're looking at a rare entity, you need to limit your number of variables that you're analyzing because it's going to create nonsensical results. So if there's like only 100 patient died in your regression analysis, you should try to limit to just 5 variables. And then when you're comparing those variables, those 5 variables in the set, they should not have similar association with each other. So a good way to look at that is to do a bivariate analysis first. So you go to analyze, you go to correlate, and then you do a bivariate analysis. So I'm going to see what are the predictors of mortality, and I'm going to only take, like, let's say COPD. I'm going to take diabetes. I'm going to take renal failure. I'm going to take end-stage renal disease. I don't need this for now. I just need person is enough. So I run this now. I got table. So what this really means is that you're looking at two stuff. So COPD, diabetes. So more COPD, it's a positive value. So and correlation is 0.02. So that means that 0.2% is a relationship with mortality. Diabetes surprisingly has a negative correlation. People with diabetes are less likely to die. This is probably because there are too many diabetic patients in the data set. So let's say there are 100 patients that you're comparing, and 50 of them are diabetic, and 60 of them are diabetic, and 40 are not diabetic. So that can give you a false impression that diabetes is, because we are not looking at population data, we're looking at hospital data. There's a difference between a population data and a hospital data. So you might, for example, everyone is going to be hypertensive when they are admitted to hospital. That doesn't really mean that you'll get negative results with hypertensive. You probably will get negative results with septic shock or something worse than hypertensive. So it's mostly comparing variables with each other. Um, End-stage renal disease, you can see there's a strong association with mortality. So now when you see this, you have to pick and choose which variables you want to choose in your final model. And there are a couple of ways to do it. One is your clinical suspicion. If you have a strong clinical suspicion, this doesn't really matter. No matter how your association is, you can add that, because a meaningful relation, even if it's weak, does count. Strong correlation, even if it's strong but doesn't make any sense, you don't need to add it in your final model. So a lot of people kind of either skip this process, or you can just make it an arbitrary. I'm going to say I'm going to take everyone who's above 0.01 correlation and a p-value of less than 0.01. So all of these variables fit that criteria. Now I was saying that two variables should not be related with each other, remember? So you have to also select that as a thing. So renal failure and end-stage renal disease might be correlated with each other too much. Here, there's no real strong correlation. Like it's 1 and 0.264, so that's not a very strong. It is some relation, but not very strong. Remember, like here's 0.02, this is 0.26. So you also have to select another cutoff. Let's say I'm not going to take any variables if their correlation with each other is 0.26. The reason is because it becomes double counting. So renal failure and stage, if you put both of them in the model, you're double counting. Like you're also counting the same thing twice, and that can create mathematical errors. So these are the basic assumptions that you need to keep in mind. And a lot of people don't keep this in mind. That's why you get weird results in your regression. So bottom line is select limited variables and make sure they're not related with each other. Um, in a large data set, you don't need to worry too much about this. As long as you select, pick and choose only a few variables, like 10, 12 variables. Don't pick and choose everything. Once you do that, the rest is pretty easy. You do regression analysis, you're looking at people mortality significance. You pick and choose whichever variables you think are significant. So let's say CHF you think was significant by doing this and using your common sense and different. And then you simply add them. These are all like created, so you can simply add those variables. Here in categorical, you all of them are categorical variables. Here is your reference category. So usually it's the first reference category, but um, make it understand I'll select a variable that has more than one category. So race, for example. So when I choose first, it means that when you have results like this, you go to options, you select confidence intervals. These are all significant tests that usually we don't do. So what this really means is that um, this 0.4, the 0.58 odds ratio, the comparison is the first group, which is in NIS, it's white race. So white race is 1 and the black is 5. So as compared to whites, this is what is the ratio of mortality in blacks. So blacks are less likely to die in this group as compared to whites. Hispanics mortality is higher. And that makes sense, right? Aortic stenosis is mostly a white disease, and that's why you see this trend. And this is your p-values for that. So when you're doing, so that's what I said, select first, so it's you can remember and you can compare. So CHF is related with mortality here. Now the more variables you add, the broader this confidence interval will become, just because the mortality has limited events. Here there are only 4,400 mortality events, so pretty large events. But anyway, that's something to keep in mind. Once you get this, you just put it in your R and you can create a plot. There's several ways to create plot. You can also create it on Excel. That's a bit difficult, but you can do it even through Excel. Um, or you can just put it in a table and present it as a table. I usually use simply R. So to do that, we have only 10 minutes left. To do an R thing, let me see if we have any. So you just open an R history file and you just copy paste the data. I think we'll talk about this later. This is going to take too much time. But you can use R to create a figure. So for now, I'm just going to talk about Excel. How do I make figures in Excel? So I'm going to open a ready-made project. This is a ready-made project. Usually what I do, I look at number of, for this is a comparison between TAVR and valve TAVR and redo SAVR. So I'm comparing how many patients got which procedure. And this is a cumulative graph, bar graph. So what I do is simply paste the data here. This is the data that I got from SPSS. And then I just go to insert and I insert a table, a bar graph, just from here. So you can choose a bar graph, you can choose a stacked column graph. So how do I get this data? That's what I'm going to just talk about. Excel is just pretty simple. If you guys play with it, you will learn very quickly. So I'm not going to talk a lot about Excel. But in Excel, you just create the two groups. You put their data in. This is one data, this is second data. And then you put the x-axis here, which is your year, and it's going to create the rest of data by itself. You just highlight, insert table. There you go, it created a table. There are different type of tables you can create. So this is basically a simple Pearson chi-square, but it's you comparing a subgroup. So again, you go to analyze, cross tabulation. So I want to compare how many people died So let's do something like cost because that's what these tables were about. These are usually trends. So I have to look for calendar year. So I'm going to see in AFib how many people's, what's the cost of AFib versus non-AFib population. And then you can do mortality trends. You can also do other trends. Oh, it's taking a lot of time. I might have done something wrong. And a lot of this is trial and error. You probably would not, I think I did something wrong. Basically, from this session, I would like expect you guys to understand the concept of regression, how to create basic tables, how to get medians and means, and then general understanding of a data set. So, like whatever analysis you're doing, you're assuming that all these patients are like all of this. Like you have to know that there's a bell assumption and everything. This is your basic analysis. I think next meeting I'm going to talk about how to make figures and how to use R. Then afterwards, I'm going to talk about extracting data and coding. Basically, you use codes. These are like codes to extract data. Hopefully, next meeting we can talk about that as well. So, first step, I would say like make sure you can analyze a data. Somebody gives you a ready-made data, you can analyze it, and you can do regression analysis on it. And you can create a forest plot for that, which I think I'll talk about next time. So yeah, I think that's it. We're running out of time. So next time I'm going to teach you how to do a forest plot, how to do Excel figures, and how to extract, how to do basic coding, and then how to extract data. And then afterwards we can repeat regression analysis again. I'll do some examples, and then we can also do propensity matching. So I hope this is a bit helpful. It's pretty, some of you guys would know most of this stuff, some won't. Do you guys have any questions on this topic?
So questions arise when I start doing it. Thank you
Yeah,
for the
and this is going to happen. Just hit me in chat whenever you have questions. Just practice on this table. I think I would expect you guys to start making tables first. That's something that because if you make a table and then you write that result, that's like 50% of work. Regression is like another 25% of work. Because tables are pretty large and they take quite a bit time. Like they take at least half an hour, not a lot, but at least half an hour. The biggest problem is you have to be very meticulous. You can do mistakes in it. So, but if you just use the tables the way I showed and you just copy paste, there shouldn't be a lot of errors. So you can probably make this table in like 20 minutes because you can just simply select all of these and just drag and then just select these. So like these three columns you can do very quickly. And the p-values also comes up at the end of the table like we saw here initially. Yeah, I told you I did something wrong here. That's why it's showing it. So the AFib should have been so That's pretty much it. Maybe tomorrow or maybe next month, depending how the service goes. Any questions? I'm going to end it, I guess.
Sounds good. Thank you very
Okay.
much.
All right.